Okay, welcome to this video about what net ionic equations are and how to write them. This is the first part of Unit 1 in AP Chemistry this year. Okay, so first you need to understand what I'm talking about when I say net ionic equation. If you were to react lead to nitrate and sodium iodide, you'd quickly see a yellow precipitate form, and that yellow precipitate would be the thing that captured your attention. And so if we want to show what's going on in a reaction, but we want to show the important stuff that's getting formed, the important product that's getting formed, then we want to show just the precipitate. So normally in regular chemistry we write the molecular equation where all of your compounds exist as intact compounds, and then sometimes you can have these states of matter beside your compounds to indicate if you have an aqueous solution or a solid precipitate. And that's great and wonderful. That doesn't really give you a particulate idea of what's going on inside of the reaction. So what you need to do is any place where you see AQ, that means that that solution is aqueous. That means that that compound was a solid, it was put into water, and when it was put into water, it dissociated, it pulled apart into positive and negative ions. So the second equation is sometimes called your complete or your total ionic equation. And any compound that is in aqueous form can be separated into positive and negative ions. So that's shown here in the second line. And you'll notice that a couple of things. One, the product here, this lead 2 iodide, it's a solid. And it does not get separated into ions because it's forming this insoluble solid product over here. Second thing I want you to notice is that your sodium and your nitrate ions are canceled out on each side of the equation. So those are spectator ions. You'll notice that nothing happens to the sodium in the reaction. You started out with sodium ions and you ended with sodium ions. Same thing for nitrate. Started out with with nitrate ions and you ended with nitrate ions. So those are called spectator ions. They don't participate in making a solid precipitate or a gas or a liquid. They stay as ions. And when you have the same ion present on each side of the equation, you can cancel those out because they're not changing at all. So the sodium and the nitrate are not changing. So once you cancel out your spectator ions, you're left with the overall net ionic equation. Here's what happened in this reaction. This is the stuff that's important. This is the big change that I saw. So you have lead, your lead ion, your lead 2 ion did not get canceled. Neither did your iodide ion. So that stays, and that formed the solid insoluble precipitate lead 2 iodide. And that this last equation right here is your net ionic equation. It includes any reaction species that are not spectator ions. So if you want to see this on a different level, this is a different reaction. This would be the reaction of sodium chloride, so NaCl, with silver nitrate, AgNO3. And when you put sodium chloride into solution, it'll split into sodium ions and chloride ions. And then you've got silver nitrate that will also dissociate into silver ions and nitrate ions. But when you mix these two solutions together, you'll start to see the formation of a white white silver chloride precipitate. And that will be a solid, and you'll see that solid. Nothing will happen to the sodium or nitrate ions, so they will continue to be your spectator ions. So in your net ionic equation, your sodium ions and your nitrate ions will really just be spectators, and you can cancel all of that out, and you would just keep your silver ions and your chloride ions, and then you got your solid silver chloride product. So again, the net ionic equation includes the reactants that make any product that is a solid a liquid, or a gas. Okay? So right now you may be asking yourself, well, how do I know if a compound is going to be a solid, or if it's going to be aqueous, or if it's going to be gas? Usually, for the reactants, you're told through the description of the equation, a solution would be aqueous, or if it says solid potassium chlorate, then you would write solid. For organic compounds that have hydrogens, carbons, and oxygens, um, typically those are going to be gases or liquids. So you'll have to kind of read some context clues to get that. In terms of the products, if you'll remember Cashin Gia, so any uh, salts with chlorate in them will be soluble. So if you see ClO3, that's going to be a soluble substance. It's going to be aqueous. Acetates are soluble, and I'll point out one exception in just a minute. So if you have um, salts of acetates, they're going to be soluble and they're going to make ions. Sulfates are soluble and they'll make ions, they'll dissociate, except when sulfate is with calcium, barium, strontium, or mercury, silver, and lead. Okay, so they're not going to be soluble in those cases. Halogens, your group 17 elements, those are going to be soluble unless they're with what I call the heavy metal bad guys, mercury, silver, and lead. And those heavy metal bad guys appear in a couple of places. Nitrates, soluble no matter what. Group 1 metals, so starting with lithium and working your way down that first group, they're going to be soluble and dissociate as well, so they'll make aqueous solutions. So over here on the right, you've got sort of the spelled out form of these rules. And one thing I want to point out, sorry about that, one thing I want to point out down here, you've got hydroxide salts. So if you see hydroxide in a compound, they're usually soluble with group 1, and they are soluble with calcium, barium, and this is not on here, but calcium, barium, and strontium, they're soluble with that. They are not soluble if you have magnesium hydroxide or beryllium hydroxide, okay? And then down here you've got carbonate. Carbonates are not going to be soluble unless they're paired up with the group 1 metal. So you're going to be able to use this solubility chart on your test for this first part of the unit so you can get comfortable with it. But you want this close by while you're working on your net ionic equations so that you can predict the states of matter of your products.